In this video, we're going to go over section 6.3 from our textbook, which is on properties of logarithms. So we'll start with this property here. For all positive numbers a that are not equal to 1, a to the power y is equal to x is equivalent to this log function here, y is equal to log base a of x. Now this expression, log base a of x, represents the exponent to which the base a must be raised in order to obtain x. And so our exponent is y here, and y is equal to this log function. Now we know that the number a is going to be the base of the logarithm, and x is called the argument of the logarithm. Now this argument x here must always be positive. So let's look at some examples here. For example, 2 cubed is equal to 8 can be rewritten as log base 2 of 8 is equal to 3, just following this property here, and similarly for these examples here. So what we'll do is we'll use that property to solve the following log equations. For this example here, part A, what we're going to do is rewrite this guy using this property here. Doing so, we'll get 4 to the power x is equal to 256. We saw from the last video that if our bases are the same on both sides of our equation, then we can set our exponents equal to each other. We know that 4 to the power 4 is equal to 256, so we have this here, and we know that we can set x is equal to 4 here. So that's our solution for that guy. Let's do the same thing for part B here. We're going to rewrite this guy using the property we just used. This tells us this guy can be rewritten as 2 to the power 5 is equal to our argument x plus 8. We know that 2 to the power 5 is equal to 32. And so solving for x, we'll just subtract 8 on both sides of our equation. So we'll get x is equal to 24. All right, and then lastly, looking at this example C here, we'll do the same thing. We'll have 4 to the power 3 over 2 is equal to our argument x. Now doing some properties of exponents here, we know that this is equivalent to 4 cubed to the 1/2 power. We also know that 4 cubed is going to be equal to 64. So we get 64 to the 1/2 power. And we know 64 to the 1/2 power is the same as taking the square root of 64. So this tells us that x is equal to 8 here. Alright, so that's how we can use that property to solve log equations. Now the next thing we're going to look at are two different types of logarithms. So first we have the common logarithm here. So for all positive numbers x, if we have log of x, this is the same as log base 10 of x. So whenever you just see a log by itself, we're always assuming that it's of base 10. And on the other hand, we have our natural logarithm. So for all positive numbers x, ln of x is equal to log base e of x. All right. We also have some inverse properties for these guys. So log base a of a to the power x is going to be equal to x for all real numbers x. And this is because the log base a and taking an argument of a, these guys undo each other. These guys are inverses, so this x just drops back down and we're just left with that guy. Similarly, if we take log base a of x to the base a, so we take base a of log base a of x, these guys cancel again, this x drops down, and we're just left with x here. Similarly, if we were to take base e on both sides of this guy, right, we know that if our bases are equal on both sides, then our exponents are equal as well. So taking base e on both sides of this equation does not change the value of this equation. But we can see that since ln of x is equal to log base e here, if we were to take base e on this side here, we know that this is going to cancel based off of this inverse property here. And so this guy's going to cancel too. So we have x is equal to x on both sides of our equation. All right, and this is because e and our natural log here are also inverses of each other. So we're going to use these properties here to evaluate these expressions. We'll start with ln of e to the 5th power here. Using what we just discussed about our inverse properties, we know since ln of x is equal to log base e of x, ln of e to the 5th power is going to be log base e of e to the 5th power. Since log base e of e, these guys are inverses, this 5 in our exponent will drop back down, and so this will just be equal to 5. Similarly, here we have log of 10 to the 8.7 power. Remember we said with our common logarithm, if no base is written there, then we assume that this is going to be log base 10 of 10 to the 8.7 power. And these guys are inverses of each other, as we see here. So these guys cancel and our 8.7 drops down. And we get that there. And then lastly, looking at this example C here, for the same reasoning as in example A here, we just know that our exponent is going to drop back down. We know that the ln and e undo each other, and so we're just left with 3 over 7. All right. Now there's several other properties of logarithms that we're going to look at today. For example here, if we have a number a that's greater than 0 and not equal to 1, then log base a of 1 is equal to 0. Log base a of a to the power k is equal to a. We just saw that with our inverse properties, and similar with this property 3 here. Now with property 1, it might not be as obvious, so we'll do a quick example for this guy. Let's suppose we have log base log base 3 of 1 is equal to x. Now, rewriting this using the very first property that we saw, we know that this is going to be 3 to the x, and that's going to be equal to 1. Now, the only way that 3 to the x will be equal to 1 is if x is equal to 0, because anything to the power 0 is equal to 1. So whenever we have a log function of this form, this x here is always going to be equal to 0. All right. And then our last 3 properties here are the product, quotient, and power rules here. So if we have a log function like this, log base a of x times y, this is the same thing as log base a of x plus log base a of y. Similarly, if we have log base a of this guy here, x divided by y, this is the same as log base a of x minus log base a of y. And lastly, our power rule here, if we have log base a of some x value to the power r, this r can come down in front of our log function and be rewritten like this. So we'll use these properties here to do several examples. In the first example here, we want to use these properties of logs to rewrite this expression. Well, since we have log base 3 of some quotient here, this tells us we're going to use quotient rule. Using quotient rule, this will be log base 3 of 5y minus log base 3 of z. Okay. Notice though, we do have log base 3 of 5 times y. Since we have a product here, this tells me we're going to use product rule. So this will be equal to log base 3 of 5 plus log base 3 of y. And then we still have this minus log base 3 of z on the end here. Right? So that's as far as we can go to rewrite this expression using these properties. Let's do another example here. We again have a quotient, so I'm going to do quotient rule. We have log base b of x times y squared minus log base b of z cubed. Again, I have a product of x and y squared, so we're going to use our product rule, same way we did in the last example. Now, notice that both of these terms here have a power in them. So this tells us we're going to use our power rule. So we'll rewrite our powers like this here, bringing the power down in front of our log function. Like that there. Alright, so that's how we would rewrite that expression. And lastly, what we want to do is pretty much do the opposite of the last examples. We can think of these expressions here as condensed versions. We just have a single logarithm with coefficient 1 in front of it, and this is very condensed. And as we can see here on the right-hand side, what we did was expand this expression. Okay, so this is a condensed version, and this is the expanded version of this guy. In these examples, what we want to do is we start with our expanded version, and we want to rewrite this guy as a condensed version as a single log with coefficient 1. So we're going to use the properties that we just saw to condense this guy. So looking at this term here, I see there's a 2 in front of our log function, so this tells me that we use the power rule here. So to undo that, I'm going to bring the 2 back to this power here. All right. Now, we also have a sum of 2 log functions here. And remember, we want to write this as a single log, so we're going to condense these guys. And since we have a sum here, we know that we used the product rule. So we're going to rewrite this sum as a product. So this will be equal to log base c of z plus 1 squared times 3z plus 6 here. All right, and we're done. We wrote this as a single log with coefficient 1, so there's nothing further to do to condense this guy. All right, and this is our last example here. We want to do the same thing. We want to condense this guy. In this first term here, we have 2 times our natural log of x. So this tells us that this 2, we use the power rule. So we're going to bring this 2 back to the power of x here. So we have ln of x squared. And on the second term here, we again have our 6 out in front of our natural log function. So this tells me to condense this, we're going to get ln y to the 6th power. And lastly, we have a difference of these 2 natural log functions. So this tells us we can use our quotient rule to condense these guys. So we'll rewrite this difference as a quotient here. So this will be ln of x squared over y to the 6th power. So we've rewritten this as a single log with coefficient 1, so we're done with that guy there. Alright, so that'll be it for this video.